Hello, good afternoon. Thank you very much for joining me in this next session. I'm very excited to be here, my first time here at Davos, Belgium, and I'm thoroughly impressed by all these halls and the entire event. It's an incredible experience. So today we are going to talk about connecting physical devices to the real-time web, enterprise-grade WebSocket for the Internet of Things. I am Peter, and I live in California. I was born and raised here in Europe. Have been living in California for about 13 years. And I work for a company called Kaazing. Kaazing is based out of San Jose in the Silicon Valley. And Kaazing's major contribution to the software world is that the founders of the company pioneered the WebSocket standard. I'm going to say a couple of words about what those contributions were, but there were basically the founders made WebSocket web-friendly and made it successful despite some previous failed attempts to bring the notion of sockets to the web. Okay, so my role at Kaazing is to stay in touch with the developer and architect community and to inspire all of you, build solutions and demonstrations that show how far we can stretch the technology. So I wanted to get started with a handful of demonstrations. My assumption is that most of you have played around, tinkered around with WebSocket, so do have some experience with it. So some of the demos that I'm going to show may be familiar, some others may hopefully be new. And after taking a brief look at some of the capabilities of WebSocket in the notion of the web and web browsers, we are going to move on and see how we can take it to the next level. So the first demo that I'd like to show is going to be a live demo. Most of them are going to be. And we're going to try something we haven't tried before. I have a browser here on my laptop, and there is a canvas tag rendered in Chrome. And there's a ball bouncing there around. And now I take my iPad and I load the same page. And as I load the same page, hopefully we can get the two kind of side by side. And I tap on the iPad. The two screens connect and the ball bounces across. This was the first demo that I built, and when I saw this, I was like, this is quite impressive. And it's even more impressive if you know that the server that we are going against is out there on the public web. You can try it out yourself with two of your phones. And the server is in the US. So what's happening here? Whenever the ball gets to a common edge, then instead of bouncing the ball back, a message is sent out through the WebSocket server telling the position, the speed, the direction of the ball, telling the other browser, hey, take it over, and you render it from here on. Okay? So this is the kind of the simplest little demonstration, and hopefully a little different than what you have seen in the chat examples before. Let me show you another one, a little more businessy demonstration. And this one is a foreign exchange dashboard that displays data coming from a simulated backend data source. A foreign exchange dashboard displays currency pairs that allow people to trade on them. Here you can see about 90 to 100 messages coming in per second, and you see the speed with which it's coming in. Again, it's going against the same server. Now, if you wanted to open the same URL on your mobile device, regardless whether you're on Wi-Fi or you're on your cell network, you would see a very similar experience over there. Again, as you would expect, no extensions, no plugins whatsoever. Let me show you another example, and this one is about synchronizing experiences. So what you see here is my laptop, and I am bringing up a web page on the laptop, and I'm leaning my iPad against the laptop. And I turn on the laptop, bring up Safari, and navigate to the same page. And as the page comes up, I start interacting with the images, and I'm moving them around, and this is a synchronized experience you get over on the other side. So this is something that can be done or can be leveraged in a number of different ways. You are doing something very similar when you are editing Google Docs at the same time. One person is editing one paragraph, the other person is editing the other paragraph. Okay, and now we take two of these images on the tablet and we move them around with a multi-touch. Now this is not something you would be able to do easily on a laptop touchpad or on a mouse. And now I'm moving over to the laptop, and I use the touchpad there to move things around, and you see on the iPad things are reflected. And here I'm getting ready to the highlight of the demo, where with one of my hands I'm going to move one of the images, and with my other on the iPad, and with my other hand I'm moving the image on the laptop, so you see the full bidirectional nature of the communication, data flowing seamlessly back and forth with a very, very low latency. So this was another example. Let me show you one more. This one is more from the media and entertainment space, where we are watching a sport event, and as we watch the sport event we have a mobile device. I mean, very often we find ourselves Googling and tweeting and Facebooking as we watch these events, but you can very easily build second screen experiences where whenever something interesting is happening in the arena, you can swim in some questions, and notice how synchronized it is. Question swims in the same time on the mobile device. On the mobile device you can wager, you can set your pick. Is this going to be a ball or a strike? Sorry for the US sport here. And eventually when the time ticks down, whenever the event happens, then the correct answer shows up both on the big screen as well as on the mobile device, and the leaderboard gets updated instantaneously as well. So this is a second or another example. Let me show you one last example that is kind of interesting. What you see here is a WebGL rendered race car on the screen. I can control it with my keyboard. I can move the car around. And now I'm going to take my phone and I'll connect. I open a web browser on my phone, and I connect to this car or this web app running inside the in the browser. And now, as I am tilting my phone left and right, I am tilting the wheels of the car, and as I am tilting it forward, I can start driving it around by simply tilting the phone. So what's happening is events are firing as I am tilting the phone, and these events are published out, are sent to the WebSocket server. The car is listening on those events, on the messages, and just like you control the car, these messages control the car in the screen. Again, this is something you can try out. So if you go to this URL, it's running live on the public internet right now, so you can give it a try. So these are a handful of demonstrations that show what this technology can do for us. And before we move any further, I wanted to take a few minutes to review what allows us to do this. But before that, let's talk a bit about the web that we work with today, or how we are dealing with it today. The key player in this in the story is the browser. We tend to treat the browser today as a pretty dumb device or a pretty dumb piece of software. We generate the markup for it, and all we ask from the browser to render that. Not only that, the browser is separated from the middle tier by a half-duplex request-response based protocol, And whenever there's a request that is going in for the middle tier that is mainly responsible for rendering the actual markup, it has a full duplex communication with the backend, but with the browser it only has a half duplex communication. So I'm not going to go through all the challenges and issues with this. You are all intimately familiar with all these challenges. And the good news is that now there is an open industry standard, has been around for since December 2011, so for 3 years now, that allows us to do things in a different way and in a number of cases a way better way. The WebSocket standard has a dual nature from a standard perspective. The standard defines both the wire protocol that is controlled by IETF, as well as the very first language API was defined by W3C, the JavaScript API. What we need to know about it is that it basically brings the power of TCP to the web. It was designed to allow web applications to be just as capable and just as rich and powerful as TCP network applications. So you get a single socket connection that gives you full duplex communication. Given that the overhead is way, way lower, because WebSocket is a very efficient and very lean protocol, in some cases it can be 100 times less overhead that you're sending over, especially when you have scenarios of a lot of small messages going back and forth. The overhead can be extremely big when you are doing HTTP. And as you have seen in the demonstrations, the latency characteristics can be very low, and very much like HTTP, WebSocket has a TLS tunneling capability, so the WebSocket protocol has a counterpart, WebSocket Secure WSS. So what does this mean to our architecture? Well, what it means is that in addition to having a full duplex bidirectional channel between our middle tier and our back end, now we can have a full duplex connection between our client and the middle tier as well. Now here the client can be browser client or can be other languages as well, can be native mobile clients, can be desktop applications, Java, C, what have you. In addition to having a bidirectional communication channel between our clients and our middle tier and all the way back to the back end, we also have the power of HTML5. The main point of HTML5 over the web was to empower real applications in the browser without plugins and extensions. And if you take these two concepts together, you can start building applications where the markup rendering does not have to happen over on the middle tier. So very often what happens is that through HTTP, static assets and resources are downloaded into the page. That's basically getting the application into the client. And once you have the application in the client, the dynamic application-specific behavior can happen over a bidirectional communication channel. So if you think of the racer demo, where we had the race car up there, initially we got all the assets, all the WebGL stuff, all the images, JavaScript, CSS, markup, HTML into the page. And after that, there was no more HTTP communication. The browser did not send requests for assets to the server. It was sitting in a very, very much an idle fashion, and it was waiting for the control messages to come in, and that's what controlled the car. So it allows us to build very different kinds of applications. If you actually take a step back, the architecture you see here is much more close, much closer to the traditional client-server architecture than it is to the web that we live in today. Basically, you have a client, you run your application on the client has a full duplex connection all the way to the back end. Initially, it's over WebSocket, then later on, it's typically over TCP, and then you can access your backends that way. So there is no markup rendering in the middle tier. All that heavy lifting can be done by the client, and this also means that you can make your application scale a lot more. You can take your application logic and move it over to the client. Okay, so what does this API look like? So for us as developers, we are mainly interested in the API. So I wanted to very quickly run through the JavaScript API, given that that was the first standard that came out. Basically, you can create a socket connection using the WS scheme or WSS scheme, and then you can register event listeners. These event listeners are the functions that get invoked whenever these certain events happen. So when the connection opens, then we can display some message. When a message comes in, or when the connection is closed by the server, then on the client we can react to all of that. So the second half of the APIs, and this is it, you can send messages and you can close the connection. This is pretty much the API. This is pretty much the WebSocket API. It's extremely simple on the one hand, and it's extremely low level on the other hand. WebSocket was designed to support richer, higher level protocols on top of that, and we're going to talk about that. The best way to think of WebSocket as it is very much like TCP in a web context for the web. Okay, the other aspect of WebSocket is the protocol itself. The protocol itself is what made or what is making WebSocket so successful. WebSocket connection starts its life as an HTTP connection. The beauty of this is that everybody speaks HTTP on the web today. So if a browser wants to speak WebSocket, it would need to indicate its desire to the server. The server would respond that, yes, I do speak WebSocket as well. At that point, they drop the HTTP connection, and the full duplex WebSocket connection takes over the place. So WebSocket, the first three letters of the term WebSocket are probably the most important, where it is a web-friendly socket connection. And by web-friendly, we mean that HTTP is what initiates the connection, and also WebSocket is capable of using the same ports, port 80 and port 443 by default, same ports that are already open on the existing web infrastructure for communication. The magic under the covers is the standard defines that we need to use a special HTTP header called the upgrade header to express the client's desire that we want to speak WebSocket, and then the server would recognize that, and if it speaks WebSocket, it can respond back confirming that a WebSocket connection is going to take place. Now, one of the challenges with anything communication is that it's pretty hard to see it. Most of the time it's under the covers. So I wanted to show you very quickly how you can visualize WebSocket. So if we go to the Chrome DevTools, and I go to websocket.org and go to the echo test. This is a kind of a generic test page that you can use to test your WebSocket or some of your basic WebSocket logic. We have the ability to create a connection here, and after we have connected, we can send a message. And what this echo service does is, on that pipe that was created, whatever message we send, it is echoed back to us. So we send a message, and it comes back in blue. Okay, so now in Chrome Developer Tools that I just opened, we can go to the Network tab, and we can take a look at our we can filter for our WebSocket request. There is nothing else really here. And here you can see the outgoing message and the incoming message in the tools. So we can say something like, hello Devox. And when we send it, then here we see it in the Chrome Developer Tools. Again, to get here, you need to be on the Network tab. And if you have too many requests over here, then there is a filtering feature here on in the DevTools. So this is one easy way to visualize WebSocket. Okay, so we've seen the very basics of WebSocket. Now, let's take a step back and think a little bit about networked applications. Whenever we are building an application, a thick client application over TCP, we build a chat application or an email application, we would never go against TCP natively. We would use higher level, richer business protocols. We would use Jabber or XMPP for presence and instant messaging. We would use IMAP, SMTP, POP3 for email kinds of applications. Now, kind of the same concept applies in the world of WebSocket. So HTTP is running on top of TCP as well. But when we take WebSocket into this picture, WebSocket fits best underneath these business protocols. So if we want to run these protocols over the web, now with WebSocket we can do that very easily. So this means that you can, let's say, build an XMPP chat client in a way that your chat server does not even necessarily know that it is the client that is connecting over the web. So protocol layering is a very important concept in this world. How do enterprises use this these capabilities? So first of all, you have your clients. These can be browser clients, but as we'll later see, they do not have to be browser clients. And then over the public web, they would need to connect to a WebSocket server. Very much like HTTP needs an HTTP server, HTTP clients are connecting to HTTP servers, WebSocket clients are connecting to WebSocket servers. And then in typical enterprises, you do have message brokers, enterprise service buses that do the integration within the enterprise. So you have all these backend systems, these loosely coupled systems that are talking to each other. And what you can do with this new bidirectional rich communication pattern is that you can extend the reach of these enterprise systems in a very seamless fashion all the way to the browsers and mobile devices. So what this means is, in the case of the foreign exchange demo that you saw, we did have a feed that was a simulated data feed that published all its data to a message bus, and that data through a WebSocket server was published out through the web. In our case, we were using JMS. JMS is the Java PubSub messaging API, and we do have a Kaazing offers a JMS API for different kinds of clients, not only Java clients, but JavaScript, .NET, or other clients as well. So let's take a look at such a JMS app, just so we get an idea about the API. So what you see here is JSFiddle. We are still running on the web heavily. JSFiddle, if you're not familiar with it, is a nice little hacking tool that allows you to paste your HTML code in one panel, your JavaScript code in another panel, your CSS code in a third one, and the result is displayed down here. So what I'm going to do is scroll down and take a look at the messages. You can see that we have connected to a WebSocket server. We created a JMS topic here. We connected a producer, or created a producer, a consumer, and we are ready to publish messages. Now I'm going to open the same URL in another browser. And I will start interacting with it. What you see up here is a little slider and the image. So what the slider does, it changes the size of the image. And whenever I make a change to the size of the image, that message gets published. So now the size is going to be 300. This guy over here received 300 because it expressed desire to receive that message. It's subscribed to the same topic, and now it is changing its size as well. So this is an overly simplistic little example, and then obviously you can move things around. You can come over here and do the same thing. Let me try to position things so that you see the other image, so it can go back and forth. Okay. Now this is in JavaScript. Let me show you what this API looks like. So in this world, you would need to create a web page. The web page contains the image. In addition to the image, we have the slider, and we have the log messages. These are 3 different divs, or 3 different elements. And in addition, we have a client library, and this client library does the magic of introducing basically the JMS API into our application. What do we have in the JavaScript? In the JavaScript, if you're familiar with JMS, this might be something for you. If not, then excuse me for just for this single slide. First, what we do is we create a connection factory. And let me see, excellent. So we create a connection factory, and we feed into this connection factory the WebSocket URL that was designed or defined somewhere further up. We are using STOMP, the Simple Text-Oriented Message Protocol, as the wire protocol, and we implemented the JMS API on top of that. And then we create a connection. And in the world of JavaScript, you do have the notion of callbacks. Whenever the connection gets created or there is an exception, then this function gets invoked. And ultimately, we get a handle to the connection. Once we have the connection, we can go ahead and create a session. If you have done JMS, this should sound pretty familiar to you. Once we have the session created, we create a topic. We create the producer, we create the consumer. So in this application, we are both consuming and producing data. And probably the most important part is how we deal with the messages. So what we define here is an event listener that says this is the function that needs to be invoked whenever there is a message coming in. So if you think of the race car, whenever control messages were coming in, this was the function that kind of fed the UI how the car should be controlled. And then we start receiving the messages, and the first message that we send is hello world. So this is basically the very simplistic API. We are introducing higher level, richer capabilities on top of WebSocket, this time with the help of JMS, but it could be any other PubSub protocol. It could be MQTT, it could be Stomp, AMQP, or any other protocol. So this is a good time probably for a little plug. With two of my colleagues, I wrote a book on WebSocket. Actually, this was the very first book on WebSocket that kind of follows the path of what we just talked through. It talks about the WebSocket API, talks about the WebSocket Protocol, as well as a number of different protocols on top of WebSocket, including XMPP, Stomp, and VNC, the Remote Frame Buffer Protocol, security and deployment considerations. So if you are interested in getting this book, at the end of the talk, we are going to do a quick raffle. And all you need to do is register here on this URL. I put this on the bottom of the deck as well. Now, if you are not into books, which I can understand, then I brought something for you. I brought 3 of these excellent baseball caps. And last, if you are not into baseball either, I have this power pack to charge your mobile phone when you are on the road, kind of as a little backup. So this is what we are going to raffle off when we are done here. Okay. So let's talk about how we can stretch the limits of this awesome technology. How can we take this to the next level? How can we connect physical devices using the open and public web in real time? So the first thing we need to do is, we've seen that this was all software. How can we get to the world of hardware? We need to operate motors, and we need to listen on sensors and all these kinds of things. So there's a wide variety of options available to you. I'm going to show 2 approaches that we have looked into, but you will see that the pattern is actually very similar. The first one is the Raspberry Pi. Probably most of you have played around with it. It's a credit card-sized little computer, can run Linux, can run the JDK. It's pretty awesome. It has an Ethernet port, it has several USB ports, it has an HDMI out, and the most important part is down here. It's the general purpose input-output port. And what it can do is take some software and transform that magically into highs and lows on the output pins. In addition, it can also listen to changes on these pins. So you can put switches on it, and all this can be detected in the software. So this is all very straightforward. So after we have bridged the software and the hardware, I was thinking what the simplest possible demonstration would be for something like this, and I figured that there's nothing simpler than a switch and a light. And if you can come up with a simpler one, let me know. And yes, you can connect a switch and a light directly to each other, but who would ever want to do that? So how about we connect the switch and the light to a computer each, and what we do over on the left-hand side, we are listening and detecting whenever the switch is toggled. Over on the right-hand side, we have the light, and what we can do is we can control the light. So notice that the flow of the information is exactly opposite. In the switch's case, it's the switch that publishes basically the information, that shares its state. In the case of the light, we are controlling the light. So now that we have connected the two, there is nothing that would prevent us from connecting these Raspberry Pis together. But we can, in addition or besides just simply connecting them, we can attempt and connect them over the web. So what we are going to do is we will put some Java code onto the Raspberry Pi. And this is the point where it becomes very important that the WebSocket standard is an API, JavaScript API on the one hand, that was defined first, and then a wire protocol on the other hand. It being a wire protocol, it allows us to build language support pretty much in any language. There is, for the Raspberry Pi, Pi4j is a very popular library that you can use that would give you very simple and easy access to the general purpose input-output ports over on the Raspberry Pi. So by putting a Java library onto the Raspberry Pi, we can detect all these hardware changes. And then we can also put a Java client library on the Raspberry Pi that has the ability to speak WebSocket. Has the ability to speak WebSocket, or maybe even a higher level protocol than WebSocket, while in our case we were playing with JMS. So what we ended up doing was we turned the light switch into a producer or a publisher, and we turned the light into a consumer. And by doing so, all we needed to do is connect the two Raspberry Pis to the web, and that way we basically extended the reach of the actual physical cable that we could stretch between the two Raspberry Pis to the web. Now, if you add to that the Raspberry Pi can have a Wi-Fi dongle, then all you need to have is a Wi-Fi connection, and whether you're on a space station on Wi-Fi or you are on an asteroid landing little device, it all works. So we basically set up an architecture like this. We have the light, we have the switch. The switch is the one that is publishing the data with the help of the Raspberry Pi. It all goes to the WebSocket server. Behind the WebSocket server, we have a message broker. This message broker has the responsibility of routing the messages between the publishers and the subscribers. It says, hey, it looks like the light is interested in that message. The message goes back over WebSocket to the light. Now, having thoroughly understood this very simple scenario, we can go and place the two devices on different continents, and they are connected over the public web, and we can turn our lights off even when we are overseas. Now, how cool is that? Let's take a look at and apply all these concepts to a new demo, and I'm going to show you this one. So what you see here is I have a phone, and on the phone I have a web browser, and I'm tapping the images on the browser, and I'm driving the car around in our office. We do have a little camera mounted on the car, and eventually we edited the view in there in the bottom right corner. But what you see here is two WebSocket clients. One is, and I'll stop it here for a moment, one is the phone that is publishing the messages. The other one is the Raspberry Pi on the truck that is listening on those messages. And we're controlling the truck in real time with the help of Pi4j running on there. And now here we took it to the next level. You see the two trucks. The two trucks have the two Raspberry Pis mounted on them. And here you get a chance to take a look at the very sophisticated front end of this control. And I'm tapping the arrows here, and you see that now we have two cars, and these two cars are both subscribers, consumers of these messages. So it shows you the power, how easy and how straightforward it is to plug in new devices. Now, if you think of the WebSocket API, remember what it was like? It was like send a message and handle the message when it comes in. Now, when you have a lot of clients, it can get very cumbersome very quickly if you are not using something like PubSub that is very powerful in this case. And here you see synchronized swimming between the two cars. They are driving around. So basically, we really liked the initial racer demo, and we wanted to get those, get the that view, that 3D view, into reality. So what we did actually, we bought these cars at Toys R Us, big toy store, and we ripped out all the radio control functionality, and we added the Raspberry Pi. Okay, so now we all understand what we really did here. We had the phone and we had the car. We published the messages over WebSocket. Message broker routed to all the subscribers, and voila, here we are. One key takeaway here again is that the phone was running a JavaScript client, the car was running a Java client, and the message broker had no idea that either one of these were out there on the public web. Okay, so let's move on to the second example. When commercial airliners are flying around, there is a very traditional way of keeping track of what's happening on the airplane. All the data is recorded, all the telemetry data is recorded in the black box. The black box is an excellent idea. You can always find out if something went wrong with the plane after the flight, as long as you can recover the black box and the plane. Every now and then it happens that we lose the black box along with the plane. We have no problem finding our friends or our iPads with a click of a button, but we can easily lose these jetliners out there, which is kind of pathetic. So our experiment was, what is it that we could do to liberate the black box? Is there anything that you can do to take that data and, in addition to saving it to the black box, maybe get it off the plane as quickly as possible so that you have that data rapidly? So we built a little experiment where we wanted to simulate that these airlines are flying over the various oceans and continents. So the connectivity that we would have is a satellite connection. And we wanted to build a set of dashboards that can be rendered to whoever is interested in that information, whether it's the airline authorities, whether the airline manufacturers, or the general public. So we did not quite have the funding to get a commercial airline, but what we did was we got a quadcopter. Now, in order for a quadcopter to talk to a satellite, it would have to have a satellite terminal. A satellite terminal is about the size of a small laptop. It's pretty heavy. And the quadcopter that we got could lift about 2 pounds, 1 kilogram. That obviously did not allow us to lift up a full satellite terminal. So what we ended up doing was we connected the quadcopter through an extended range Wi-Fi to a laptop, and from the laptop we got the internet through this satellite adapter. And then we flew the quadcopter. We put a number of sensors on the quadcopter. We put a GPS antenna on it. We put accelerometer, temperature, and humidity sensors. And all this data was, with the help of the laptop, published over a satellite connection and then published out to the general web. This is the quadcopter that we got. And I wanted to show you what this experience looked like, and then we are going to go through the rest of the slides. So here's a quadcopter. And the quadcopter was a DJI Phantom 2 that can fly about 700, 800 meters. And we connected to one of the 11 geostationary satellites that a company in the UK called Inmarsat is operating. The geostationary satellites are orbiting at 22,000 miles, 35,000 kilometers. And we measure the latency, how long it takes to get our messages from California, where we flew the quadcopter, to London. And what we found was that it was about 650 milliseconds. And then we took that data, and from London, we published it out over the web. And here we had a number of clients, air traffic control, aircraft manufacturers, I mentioned, airlines, and the general public. And we measured the latency, what it took to get the data from London to the slowest corners of the web. We tested Namibia, Kazakhstan, Antarctica, and what we found was that it was about 350 milliseconds. So what we got from this little experiment is that the end-to-end latency from flying the quadcopter, acquiring the telemetry data, sending it over a satellite connection, publishing it out over the web, end-to-end latency is under 1 second. You have a commercial airliner flying over the Indian Ocean. It makes a left turn, and you are sitting at the Norwegian research station on Antarctica with a Wi-Fi connected tablet, and in less than a second you know that that plane made a left turn. And this all this communication happening over the public Wi-Fi, over the public internet. That's I think pretty interesting. So here you can see the quadcopter flying. These little rotors are wicked powerful. It can shoot up like crazy. Here you see we mounted a little box. This is the box that has all the sensors in it, and I'm going to show you a photo that we took of that. And this is the dashboard that we built. In the background you see the map. The map is going to move a pixel left and right every now and then, indicating that it's moving. That's the GPS sensor. In the middle you see a compass. You see pitch and tilt in there. On the left-hand side you see speed. On the right-hand side you see altitude. And on the bottom left there is temperature. We did not send over the video data, obviously. All we were interested in is the telemetry data, but we did mount a GoPro on it just to record, and we edited that later into the dashboard. So the amount of data that we transmitted was under 512 bytes with security taken into consideration. And we did a little math, and it turned out that to get this data to thousands, tens of thousands, hundreds of thousands of clients, it would cost about 25 US cents per passenger ticket. So it can be done in a very efficient and in a very straightforward manner. And this is a selfie that we took with a quadcopter of the team that at Kaazing. So if you want to learn more about this, about the scenario that we ran, then you can find it very easily on the Kaazing website. Okay, so what you see here is the very fashionable little plastic box that has the you see the battery here, you see a GoPro mounted here, and here is the Arduino stack of sensors that collected all the telemetry data. This is the GPS antenna. We put it outside. We wanted to make sure that we have good reception. These two sensors on the top are the humidity and temperature sensors. Now this was an interesting one. This was the satellite terminal that I mentioned the quadcopter could not lift up, and I was very happy with it. We rented it online. I was running around with it and placing it to various positions until I read the little yellow warning in the bottom right corner that said, warning, microwave radiation, minimum safe distance 0.6 meters. So after that I stopped running around with that when it was on. Okay, so this was the team, and we have seen the demo and we have seen the scenario. So in conclusion, clearly this technology allows us to connect more than just web devices or more than just devices that run traditional software. I mentioned that you can easily integrate desktop applications, you can easily integrate mobile applications natively, but we've seen that you can get there in the edge. That was the truck scenario. Now, it looks like we can use the web to connect all these devices, but when we have the right tool to connect them, namely a socket connection to these devices, then we can do a way better job. Not to mention when we put proper, richer, higher level protocols, POP-sub protocols or others, then you can be way more successful. So in the world of IoT, MQTT is a very popular protocol. In the presence and instant messaging world, XMPP is another one. There are implementations for all of these. Now, you may ask, besides getting these toys, what does Kaazing do? So what I outlined here, if you have not tried WebSocket yourself, you may think that this is all rosy. If you have tried WebSocket, and I'm talking more and more people like that, you have seen and you have experienced firsthand that there are many, many challenges. There are many challenges on the scalability front. There are many challenges on the lost connection front. There are many challenges on guaranteeing that messages are getting delivered. If you are building an enterprise system, then integrating with existing security systems, infrastructure can be very painful. Developer productivity, given that the WebSocket API is very low level, can be a challenge. So there are many, many challenges. And Kaazing's hobby, or business, I should say, is to make the technology accessible, easy to use, and basically allowing you to focus on what your application needs. So Kaazing does the heavy lifting in this world. So this is pretty much the last warning. If you are interested in getting the book or maybe the caps, this would be a good time to do that, because we are getting to the raffle in a minute. So if you wanted to learn more about all this, obviously the Kaazing website is there for you. I show the tutorial, the simple JMS tutorial, where multiple clients were connected. And you can learn more about the various IoT demos on the telemetry site. So let's do the raffle. Anybody has used the jot command before? As I was planning to do the raffle, I looked it up. It's a very neat little utility. It creates either random numbers or sequential numbers this many times between this and this. So that's what we are going to try to use now. See if there are any takers for the book. Here we are. Okay, so let's see. From 7 to 98. Okay, so let's come over here. Uh-oh, there are more coming in. 99. Okay, 7 to 99. Let's see the first winner. The first winner is number 50. Who's number 50? Okay, let's see. Number 50 gets a hat. That is Yanis. Yanis the Wolf. You in the room? Excellent. After the talk, please come. You'll get the hat. Let's do number 2. Number 2 is, are we still at 99? Still at 99. Okay. 88. 88 is Thomas. Thomas Wędzinski. You here? Excellent. You got a hat too. The last hat, I think I have 3 of them, goes to number 86. Robin Echenkamp. Excellent. Okay, here we go. Next one is the power thingy for your phone. Let's see, 75. 75, Mikhail. Mikhail is here. You got the power thingy. Excellent. And now the book. Let's see. 89. 89, Mohammed. Excellent. Okay. So it looks like we have about 10 more minutes. So if you have any questions, I am happy to try to answer them. This is what I had for today. Thank you very much for your attention.